You ever get that feeling that something is just missing from our picture of the universe? That gravity, this force we think we know so well, might be hiding a massive secret? Well, let's get into it, because a wild new theory suggests we might be right on the edge of figuring it out. For decades, this has been the big, nagging question in cosmology. When we look out into space, the numbers just don't work. It's kind of like the universe is this giant cosmic scale. On one side, you put all the stuff we can see, stars, gas, dust, and it's like a feather. But on the other side, the gravitational pull we actually measure is like a cannonball. Something is seriously off. So check this out. This really lays the problem out perfectly. On the left, you've got what all the laws of physics predict. Stars way out on the edge of a galaxy should be moving slower, kind of like Pluto orbits way slower than Mercury. But the column on the right, that's what we actually see. The stars on the outer edge are whipping around just as fast as the ones in the middle. To fix this, we basically invented dark matter, this invisible cloud of stuff that's supposed to provide all the extra gravity. But what if there isn't any missing matter? What if the problem is the empty space itself? And that brings us to this really radical new idea. What if the answer isn't about adding more stuff, but about rethinking what empty space actually is? Okay, so this is called the ΔΩ Coherence Field theory. And it says that the vacuum of space isn't, well, a vacuum. It's not empty at all. Instead, picture it as this vast, invisible medium that's actually compressible and has its own background pressure. It's not nothing, it's something. And that changes everything. The core idea here is that gravity might basically be hydraulic. So imagine space is a calm ocean of pressure. When you put something with mass, like a planet or a star, into it, it doesn't really pull things toward it. Instead, it creates a little area of low pressure around itself, like a dip in the water. Other objects aren't pulled into that dip. Nope, they're pushed into it by the higher pressure of the space all around them. So gravity isn't this mysterious fundamental force. It's just an effect that emerges from the mechanics of the vacuum. It's a brilliant idea, right? But when they first ran the numbers, it hit a massive brick wall. I mean, a flaw so big, it could have killed the entire theory right then and there. And the crazy thing is, the problem was right here in our own backyard. In a dense place like our solar system, this new hydraulic gravity was way, way too strong. It completely messed up the orbits of the planets. The theory was great for galaxies, but it failed spectacularly at home. So it was back to the drawing board. And this is where it gets really clever. The theorists didn't give up. They built a fix right into the vacuum itself. They called it a chameleon mechanism. The idea is that the vacuum isn't just some simple fluid, it's a smart fluid. It can actually change how it behaves depending on what's around it. Here's how that works, and it's awesome. In a high-density area like our packed solar system, the vacuum field basically stiffens up. It suppresses that extra hydraulic force, and boom, you get the normal, everyday gravity we're used to. But out in the super sparse halo of a galaxy, where matter is spread thin, the vacuum relaxes. It becomes fluid, and that hydraulic force becomes long-range, creating all that extra gravity we need to hold the galaxy together. It's a chameleon, perfectly adapting to its environment. All right, so with that chameleon fix locked in, the theory was finally ready to take on the biggest mysteries in the universe, starting, of course, with dark matter. And here's why it's so powerful. You get two for the price of one. It doesn't just explain why stars move too fast, it does more. First, you have that direct pressure pushing on the stars, which fixes their rotation speeds. But second, the energy that's stored in that squeezed vacuum field. The paper calls it hydraulic energy density, but think of it like the energy in a compressed spring. That energy itself actually adds to the curvature of spacetime. And that is what bends light, perfectly explaining gravitational lensing. And this is not just theory. They tested it. They took a real-world case, this dwarf galaxy called ΔΩ 154, and ran the numbers. And the results? The theory's predictions for how fast the stars should be moving matched the observations perfectly. It explained the galaxy's rotation without needing a single particle of dark matter, not one. Okay, that is just incredible. One massive mystery down. But if this theory is the real deal, it has to face the other giant in the room. You know, the force that's pushing the entire universe apart. Dark energy. Could this one idea really solve both? What the researchers stumbled upon next wasn't just another answer. Honestly, it was a discovery so mind-blowing it could end up rewriting cosmology as we know it. Now, remember that chameleon thing? To make it all work, to get the galaxy rotations just right, the theory required the vacuum to have a certain minimum baseline pressure. And when they calculated what that value had to be, they got this number. Now, at first glance, it doesn't look like much, right? Just a number from a model.
But it's not a random number. It's the number. It is the precise, experimentally measured value of dark energy, the mysterious force that's making the expansion of our universe accelerate. Think about that. The exact same vacuum pressure needed to hold galaxies together also provides the exact amount of cosmic push needed to drive the universe apart.
Just let that sink in for a second. This is not some lucky coincidence. This is unification. One single property of the vacuum, a number they figured out by looking at how tiny galaxies spin, correctly predicts the acceleration of the entire observable universe. It's like finding a single key that unlocks the two biggest, most secure vaults in all of physics.
So, is this it? Is this the theory that finally connects all the dots? Well, the beautiful thing about science is that even the most elegant idea in the world has to face the music of real-world observation.
And that's the best part. This isn't just some cool philosophical idea. It's a real, predictive, and most importantly, falsifiable scientific theory. It makes very specific predictions that we can actually go out and test. It says we should see tiny, distinct differences in gravitational lensing maps. It predicts unique signatures around the shadows of black holes. We can even look for slight deviations in the universe's expansion history. This theory has laid its cards on the table. Now, we just have to go and look. Look, we don't know yet if this theory is right, but it gives us this absolutely stunning new way to see the universe, not as a cold, empty void, but as a dynamic, living medium, a cosmos where the very fabric of space-time itself might just be breathing.